Question 1. Radioactive uranium-238 produces a series of decays ending with a stable nuclide of lead. The nuclides in the series decay either by alpha or beta minus process. Uranium-238 decays into a nuclide of thorium-234. Write down the complete equation for this radioactive decay. Well, it's a little bit small there, so let's write it underneath. So 238, that's the number of nucleons, 92 uranium, goes to, and we know we're going to 234 thorium. To go down to 234, we're losing 4 nucleons, and that means we're looking at an alpha particle. An alpha particle looks like this, and that means we have to have 90 here as our answer. Instead of 42 alpha, you could, and I would probably be more comfortable writing this as well, but both are correct. Next, the graph shows the variation with the nucleon number A of the binding energy per nucleon, and this is a graph that you'll probably be very comfortable with. Of course, what we have is a very stable nucleus around about here. The most stable element is iron, and that means that iron will not undergo fission, it will not undergo fusion, and it will not undergo radioactive decay. And it's around about 56, iron Fe 56. Anything to the left of that will undergo fusion to become more stable. A lot of stuff here to the right going towards iron will undergo fission. And some around about here to become more stable will undergo radioactive decay. That's the mechanisms that the unstable nuclei will undertake to become more stable and get towards iron. Okay, let's actually look at the question. B. Outline why high temperatures are required for fusion to occur. This is actually quite a common question, and let me do a quick explanation before I give you the 2 exact marks you need to write down to get full marks on this question. Okay, so if we're looking at fusion, we're looking at 2 small nuclei fusing together to become 1 larger nuclei. Let's draw 2 small nuclei right now. That's 2 protons and a neutron. And let's just draw 2 other small nuclei, 2 protons and a couple of neutrons. Okay, they have to fuse together, which means they have to come close to each other. There's obviously an electrostatic repulsion here because similar charges repel each other. So to get close to each other, they need to come at each other really fast. And to get at each other really fast, you have to have a very high kinetic energy. So the 2 marks you need to get full marks in this question is similarly charged nuclei, lots of kinetic energy to overcome the electrostatic repulsion. Mark is linking energy, kinetic energy, to temperature. Kinetic energy is proportional to temperature. Therefore, large temperatures are required to obtain that large kinetic energy. As you're working through past paper questions, it's quite common, and that's how you get those 2 marks. C. Outline with reference to the graph why energy is released in both fusion and in fission. Okay, so let's go back to the graph. You can see that the elements here on this side that are undergoing fusion, they all have a low binding energy per nucleon. So to become more stable, the binding energy per nucleon has to increase. That's quite a big increase in binding energy per nucleon to become more stable for fusion. But similarly for fission, you can see here the binding energy per nucleon for those elements undergoing fission is less than a stable element. So for elements here undergoing fission to become more stable, the binding energy per nucleon has to increase. And that's our answer. We have to say, to become more stable, the nucleon must increase. Do something else. Let's go back to the graph. If we look at the fusion side, when the elements fuse together, energy is released, and you can see to become more stable, the amount of energy is released is to do with this change in binding energy per nucleon. So you can see that fusion releases more energy than fission does to become more stable. And that's where we finish off the question. We have to say that energy is released when the binding energy per nucleon increases. Question 2. Deuterium undergoes fusion according to the following reaction. Identify particle X. Okay, well, let's just do a basic addition on both sides. There's 2 nucleons on the left-hand side, 3 here, so there must be 1 nucleon there. There are 2 protons on the left-hand side and only 1 on that side, so we must have 1 there. That makes this particle here a proton. Right, we know it's a proton. Next, the following data are available for binding energies per nucleon. And we've got some data here. B. Determine in mega electron volts the energy released. Well, the first thing I want to notice is this is binding energy per nucleon. So if we're looking at this deuterium here, the total binding energy of this deuterium is 2 times this, because there's 2 nucleons in there. So the binding energy of that is 2 times 1.2 MeV. The binding energy of this is also 2 times 1.212 MeV. And the binding energy of this is then going to be 3 times 2.78 MeV. And there's no binding energy from a proton because it's not bound to anything. So let's take that information and actually answer the question. On the left-hand side of the equation, we've got 2 times 1.12 MeV. That's for one of the deuteriums, and we're going to do that times 2. And on the right-hand side of the equation, we've got 3 times 2.78 MeV. That gives us, if we do the quick sum here, 4.48 MeV on this side, and 8.34 MeV on this side. And if we take the change in energy, which is the energy released, we do 8.34 MeV minus 4.48 MeV, which gives us an answer of 3.86 MeV. And we can leave it at 3 significant figures because the data is given in 3 significant figures. C. Suggest why, for the fusion reaction above to take place, the temperature of deuterium must be very high. We've just answered that question in 1B. I'm not going to repeat it. The answer's there. Question 3. What gives the total change in nuclear mass and the change in nuclear binding energy as a result of nuclear fusion? Well, we know that the nuclear binding energy increases. We've just seen that in the calculation. So it's got to be B or D. And the nuclear mass decreases. So our answer is B. Question 4. A fusion reaction of 1 nucleus of hydrogen 2 and 1 nucleus of hydrogen 3 converts to 0.019 U to energy. Okay, so when we fuse together this, what we get is a mass defect of 0.019 U. And of course, we can work out what the energy of that is by using 1 U is equivalent to 931.6 MeV. I think it's 6, it might be 5. I don't think we're going to have to go as far as that. This is fusion. Let's look at fission now. A fission reaction of 1 nucleus of uranium-235 undergoes fission, and it gives out a mass defect of 0.190 U. And again, we can work out what the associated energy is by using this equivalence here. What is the ratio of the specific energy of this fusion of hydrogen to the specific energy of this fission of hydrogen? Okay, well, the first thing we need to note is the specific energy means the energy available per unit mass. So what we want to do is find out how much energy per unit mass is available for fusion and compare it to that of fission. But we already know something. We know that any fusion reaction gives out way more energy than any fission reaction. So we already know that the specific energy of fusion is going to be greater than the specific energy of fission. That means this ratio is going to be greater than 1. So we can already say A and B are out. So how do we work out the final answer? Okay, let's go to fusion. Let's work out what the mass defect per nucleon is. We've got 0.019 divided by 5, it's 5 nucleons. And that's going to give us an answer of 0.006 0.038 U. And for fission, let's do the same. Let's work out what the mass defect per nucleon is. So 0.190 divided by 235 gives us an answer of 0.00081 U. And if we pop that into ratio up here, then it's going to be 0. Pop that into our calculator, and that's going to give us an answer of 4.7, which rounds to 5. Our answer is 5. Question 5. A graph of the variation of the average binding energy per nucleon with a nucleon number has a maximum. What is indicated by the region around this maximum? The region around the maximum shows that they're stable. So we want to look for the words stable. C, the position where the most stable nuclei are found. The answer is C. 6. The astronomical unit AU and light year LY are convenient measures of distance in astrophysics. Define each unit. AU is the average, and I'll tell you why the word average is important here in a second. It's the average distance between Earth and Sun. Why do we say average? Well, if you think about the Sun and then the Earth, it's not quite a perfect circle. It can be elliptical. So at certain points, the Earth might be further away from the Sun than other points. So the average distance between the Earth and the Sun takes into account that slightly elliptical orbit of the Earth around the Sun. Light year is the distance light travels in 1 Earth year. It doesn't say in the syllabus that you need to know the definitions of both of these measures of distance. However, it does delve deeply into the parsec, and the parsec is a measure of distance. The other reason I think it's a good idea that you learn these definitions is that both of these measures of distance are given in the data booklet. So I feel like this could be something that naturally comes up as part of the exam paper. Okay, let's move on to the rest of question 6. An image of a comet is shown. Comets develop a tail as they approach the Sun. Identify one other characteristic of comets. Okay, well, they're made of ice and dust. They have an elliptical orbit around the Sun. And, I mean, that's enough, but I think they originate in the Oort cloud. I think you're expected to know that. B2. Identify one object visible in the image that is outside our solar system. So the comet is inside our solar system. We've got lots of other little dots, and they could either be stars or galaxies, and they are outside of our solar system. So it says identify one, so just put one down. You put stars or galaxies. Don't write down 2, it just says identify one. Question 7. Eta Cassiope A and B is a binary star system located in the constellation Cassiope. A. Distinguish between a constellation and a stellar cluster. Well, let's start with a cluster first of all. A stellar cluster are stars that are actually close in space. So a cluster is a group of stars that are close in space. In contrast, a constellation is a group of stars that appear close in space but are actually not. And by that I mean the distance between them is not close, whereas the distance between stars in a cluster is close. We've got some data coming up. The following data are available, and we've got the apparent brightness of both stars. We've also got luminosity, and question B says the peak wavelength of radiation from Eta Cassiope A. I don't know if I'm saying Cassiope right or not, by the way. Who knows? Is 490 nanometers. Show that the surface temperature of A is about 6,000 Kelvin. Okay, we're going to use Wien's law, which is lambda peak T is equal to 2.9 times 10 to the minus 3. You're going to use all the equations that we discovered in B2, topic B2. So we're going to use the apparent brightness, luminosity, and Wien's law. We're going to use them here. So we want to show T is equal to 2.9 times 10 to the minus 3 divided by 490 times 10 to the minus 9, which gives us an answer of 5900 Kelvin, which to one significant figure is 6000 Kelvin. It does say show that. Show that means that this number is probably going to be used later. Now, I am going to carry this number forward because that's the number I've worked out. If you don't get that question right, then you're allowed to use this number carrying forward. C. The surface temperature of Eta Cassiope B is 4100 Kelvin. Determine the ratio of the radius of A to B. So we want to find out what the radius of each star is, A to B. And for this, I think we're going to have to look at the luminosity equations. So let's put down apparent brightness first. That's an equation that involves luminosity. 4 pi d squared. I'm getting these from the B2 section of the data booklet. And luminosity itself, the equation for that is this. But A is the area of a sphere, which is 4 pi r squared. So D is the distance to the star. And R is the radius of the star. And it's just the R that we're interested in, isn't it? So instead of having L equals, so let's just add this in. So 4 pi r squared t to the 4th. And actually we could rearrange this. L equals 4 pi d squared b. So we got an equation 1 for L. We've got equation 2 for L. Let's equate them. So 4 pi squared t to the 4th equals 4 pi d squared b. We can cancel out these 4 pi's. And let's rearrange for r. R squared equals d squared b over t to the 4th. So that gives us a radius of A. It also gives us a radius of B. R squared B is equal to d squared b over t to the 4th. And we've got the apparent brightness for both. That's good. We've got the temperature of both. That's good. We don't have the distance to both, but we know that the distance to both is the same because when you have a binary stars, they're very close together in space. Say this is Earth down here. Distance to the stars is the same to both. So that's going to be useful because we're going to do this now. Ra squared over Rb squared equals d squared Ba over sigma Ta to the 4th. And then we're going to put Rb in. So it's d squared B over, which takes it up to the top, sigma Tb to the 4th. That cancels out with that. That cancels out with that. And our Ra over Rb squared equals Ba Tb to the 4th over Ta to the 4th Bb. So you're going to put all those numbers in, and when you put all those numbers in, you'll get the number 2.17, which goes to 2.2. That is the ratio. D. The distance of Eta Cassiope system from the Earth is, so the distance is this, 1.8 times 10 to the 17 meters. Calculate in terms of the luminosity of the Sun, the luminosity of Eta Cassiope A. So luminosity is equal to 4 pi d squared b, and 4 pi times squared times the apparent brightness of A, which is 1.1 times 10 to the minus 9. Pop all the numbers into that, and we're going to get 4.478 times 10 to the 26 watts. But the luminosity of the Sun, let's go back, is 3.8 times 10 to the 26. So we divide that by 3.8 times 10 to the 26, and that gives us a value of 1.18 times the luminosity of the Sun, which is 1.2 luminosity of the sun. And that's to two significant figures. Why do we want to do that? Well, next part of the question. A Hertzsprung-Russell diagram is shown. On the HR diagram, draw the present position of Eta Cassiope A. In the HR diagram, you can see on this y-axis, the luminosity is given in terms of the luminosity of the sun. So that's why we had to work out the luminosity of this in terms of the sun. You get a ruler and we go to 1.2 times the luminosity of the sun, which is very close to the luminosity of the sun. I'm going to draw a line on there. And then we know that the surface temperature of A was, let's go back. Oh yeah, look, surface temperature of A, that's why we wanted to know it, just in case. It was 6,000, so we're going to go to 6,000. And we're going to draw a line there. And that means that the position of Eta Cassiope is here. State the star type of Eta Cassiope A. It is a main sequence star because it's on the main sequence. Sticking with the theme of the Hertzsprung-Russell diagram, we have question 8. In question A, it says, identify on the HR diagram the position of the sun. Label the position S. On the y-axis of an HR diagram, it gives you the luminosity in terms of the luminosity of the sun. The luminosity of the sun is defined as 1 L dot. So we want the sun to be along this line. We know that the surface temperature of the sun is around about 5,900 or 6,000 Kelvin. So I'm going to draw a line up there. It's also a main sequence star, so we expect it to be on the main sequence. So the position of the sun is there. B. Suggest the conditions that will cause the sun to become a red giant. The red giant is the next stage after a main sequence star. The main sequence star, the main feature of that is that it's fusing hydrogen into helium. Once that hydrogen begins to run out, that's when it starts moving on to the next stage of its lifetime. And that's what we need to explain. So we'll start off with the idea that hydrogen is running out. When hydrogen fusion begins to run out, it causes the core to contract. Once the core contracts, the sun expands and the surface cools. This is the outer layer of the sun that expands. When the surface cools, it appears red. Cooler surface appears red. And it also appears much bigger because it's expanded out, so that's why it's called a red giant. C. During its evolution, the sun is likely to be a red giant of surface temperature 3,000 Kelvin and luminosity 1 times 10 to the 4, that of the sun. Later, it's likely to be a white dwarf of surface temperature 10,000 Kelvin and luminosity 1 times 10 to the minus 4. Calculate the radius of the sun as a white dwarf over the radius of the sun as a red giant. It's the same calculation we did earlier. So we're looking at L equals T to the 4th. A is sigma 4 pi r squared T to the 4th. And what we want to do is rearrange for r. So r squared equals L over 4 pi T to the 4th. So if we want to do, we're going to label the radius of the white dwarf as RW and the radius of the red giant is RR. So we want to do RW over RR, and let's keep them squared for the second, equals LW over sigma 4 pi TW to the 4th. And that's over LR over sigma 4 pi TR to the 4th. These all cancel. And what we're left is RW over RR equals the square root of LW TR to the 4th over TW to the 4th LR. And we're going to pop in those numbers. LW is and that's going to give us a number of 9 times 10 to the minus 6. That's our ratio number there. That's a very, very common question to get in the astrophysics section of Stars and Fusion, and it really originates from using this equation here. 9. The surface temperature of the star Epsilon Indi is 4,600 Kelvin. Determine the peak wavelength of the radiation emitted by Epsilon Indi. We're going to use Wien's law. So what do we want to find out again? Peak wavelength. Temperature, which is 4,600, which gives us an answer of 6.3 times 10 to the minus 7, which gives us 630 nanometers. A2, using the axis, draw the variation with wavelength of the intensity of radiation emitted by epsilon Indi. So we want to put a peak wavelength in around about 630 nanometers there. And it's got to have the curve of the black body curve, or of a tail on that side. So we want a black body curve with a peak at 630 nanometers. A2, the following data are available for the Sun. We've got the surface temperature is 5,800 Kelvin. Luminosity, mass, radius is all labelled as R dot, M dot, L dot, and so on. Epsilon Indi has a radius of 0.73 R dot. Show that the luminosity of epsilon Indi is 0.2 L dot. So L equals sigma A T to the fourth. We know that the radius of epsilon Indi is 0.73 R dot. So we can say squared. But we need to know the temperature of epsilon Indi in terms of the temperature of the Sun. Okay, well the temperature is equal to 4.6. That's the temperature of epsilon Indi divided by that of the Sun, which is 5,800, which gives us a value of 0.79 temperature of the Sun. So 0.79 temperature of the Sun to the power fourth. If we put those numbers in, we're going to get 0.21 of the luminosity of the Sun. And that's our number there. The luminosity of epsilon Indi is that. And of course, if we put the correct number of significant figures, we've shown that that's the case. Describe how the chemical composition of a star may be determined. Well, the first thing we want to do is obtain an absorption spectra of the star. And it's going to have lots of different lines in it associated with these jumps between the electron energy levels. But if we compare that spectrum to the spectra of elements, for example, hydrogen, and if the spectrum has lines in the same place, then we can tell that hydrogen is in the star. So we want to write that in a nice, easy sentence. So I think we'll compare the distinct spectra of elements to the spectrum of the star. And then we'll say, if lines match, we can assume the elements are part of the star. Question 10. Mintaka is one of the stars in Orion. A1, the parallax angle of Mintaka measured from the Earth is 3.64 times 10 to the minus 3 arc seconds. Calculate in parsecs the approximate distance of the Mintaka from the Earth. If we have the units in parsecs and arc seconds, then it's a really simple formula. It's just that. So we do 1 over 3.64 times 10 to the minus 3 gives us an answer of 274.7 parsecs. We've got to put that to 3 significant figures. So 275 parsecs. Just to reiterate that, if your angle is in arc seconds, then you can use this really simple equation to find out the distance in parsecs. There's no messing about between the units to find things out. A2. State why there is a maximum distance that astronomers can measure using stellar parallax. Let me just do a quick explanation here. Using stellar parallax, what we do is we have the Sun, and the Earth goes around the Sun. Okay? So at one point, the Earth is here, and then 6 months later, the Earth is there. And what they do is they take a star that's in the distance, and they measure the angle of the star here, and then 6 months later, they take the angle of the star there. And then using basic geometry, they can work out how far that star is. Okay, it's literally using SOHCAHTOA. However, as that star gets further and further away, that angle is going to get smaller and smaller. And if the star goes too far, the angle is unmeasurable. So what we want to say here is, as the distance increases, the parallax angle decreases and becomes unmeasurable. Question 11a. distinguish between the solar system and a galaxy. The solar system is a body of planets orbiting a central star, and a galaxy is a body of gravitationally bound stars. A2, distinguish between a planet and a comet. Okay, well, a planet, it's large, it doesn't have a tail, it's got a largely spherical orbit and might have some moons. And in contrast, a comet is a small body, it does have a tail, it's got a strong elliptical orbit and it has no moons. Question 12. The graph shows the observed spectrum from star X. The second graph shows the hydrogen emission spectrum in the visible range. Suggest, using the graphs, why star X is most likely to be a main sequence star. Okay, well, let's see what information we've got. We know the peak wavelength. We also see that we have certain dips in here where these wavelengths have been absorbed. And these wavelengths correspond with, let's see what wavelengths they are. So we've got roughly 410 nanometers. This one's around about 430. That's around about 480. And that's around about, I don't know, 650. So we've got these dips in the emission spectrum at 410, 430, 480, and 650. So these dips in the absorption spectra correspond with the lines of hydrogen. That means that this star has hydrogen in it. The dips in the observed spectrum match the wavelengths of the lines in the hydrogen spectrum. This means the star contains hydrogen, which is representative of a main sequence star. A2, show that the temperature of the star is approximately 10,000 Kelvin. So we're going to want to use Wien's law. T is equal to 2.9 times 10 to the minus 3, and I'm willing to bet that the lambda peak is around about 290 nanometers. Yep, 290. Which gives us an answer of 10,000 Kelvin. It's an easy 2 marks, that one. The following diagram shows the main sequence, and this is a different version of the HR diagram. We've got the luminosity in terms of solar luminosity here, and we've got temperature on the x-axis. Write down the luminosity of star X in terms of the luminosity of the sun LS. So what we want to do is we want to go to 10,000 Kelvin, because that's the temperature of our star X. And then we want to take it along to the luminosity and read off this scale. So that's going to be 20, that's going to be 30. So this section here is 30 times luminosity of the sun, which is the luminosity of the star. So write down the luminosity of the star. Lx equals 30 times luminosity of the sun. A4, determine the radius of star X in terms of the radius of the sun, Rs. So Lx equals so that means the radius of star X is equal to Lx over sigma 4 pi squared. Oh. So the luminosity of X is equal to 30 luminosity of the sun, and the temperature of X is equal to which is 1.69 temperature of the sun. So we can substitute this in, 30. And if we do 30 divided by 1.69 to the power of 4, then that gives us Rx and we're going to square root that, sorry. Rx is equal to 1.9 R to the sun. Now the answer scheme says that Rx is equal to 2.1 the radius of the sun, and that's because they've taken the luminosity of the Rx from the HR diagram to be 35 LS, but there's a scope of plus or minus 5 in there. So this answer is correct, and this answer is correct. Sorry, and this answer is correct. Number 13, question 13, our final question. Main sequence stars are in equilibrium under the action of forces. Outline how this equilibrium is achieved. So what we have is a main sequence star, and pushing outwards is the force that is generated due to radiation pressure. The fusion causes radiation pressure outwards. So we're going to write radiation pressure acts outwards due to fusion. And then what we have pushing in the way is gravitational force. So we'll write that down. We'll say gravitational force acts inwards. And these balance in equilibrium. These forces balance in equilibrium. And that is how a main sequence star stays in equilibrium. And you can see my writing has just come completely off the boil now because I'm completely finished. And that was quite long. But I'm glad you were with me. I hope it was helpful. And onwards and upwards.